Hi, everybody. I am so pleased to see everyone in person. And I'm really also very pleased to have the opportunity to talk about GALAH for a couple of minutes, warm you up for the science talks that are coming after me to get into some more detail of what all we've been doing, because we have been busy little birds. So how do I go forward? I'll start and end with the same thing, which is to say that the GALAH team is busy. We are collaborating, we are publishing, we are improving our data analysis. We have a lot of things on, so I'm really pleased that we're having a science meeting now, because there's a lot to talk about. So to begin with, we are collaborating broadly. And what this allows us to do is to get out of just detailed little work or just the Milky Way and get out into broader areas of astronomy research. So for example, sometimes our team members will work on hydrodynamic simulations with some of the young experts in that. And how do we compare the way we measure chemical abundances in the Milky Way to simulations of the universe? Sometimes our team will run an entire galactic archaeology program with K2 and then get together with the big names in astroseismology and publish big catalogs about ages and stellar abundances. But again, we can use to put back into the models and see what we're doing. Sometimes our students call up experts in exoplanets and say, hey, I want to work on some machine learning and I want to be able to predict the properties of planets from what their host stars are like. And so this is all very exciting, and it gets us out of our own little specialty ranges and out into bigger connections and bigger impact. One of the things that I'm really excited about is very Astro 3D relevant, is a SAMI GALAH crossover project led by Nick Scott and Jesse van de Sand last year, where they took the Milky Way analog, an edge-on disk galaxy, UGC 10738, which I'd never heard of before, but it's perfect for this project, it turns out, because it's very similar to the Milky Way in size and mass and metallicity and all of that, and it's edge-on. And so what they could do is, as a function of radius from the center of the galaxy, height above the plane, they could map out metallicity, which is the top row, alpha enhancement, which is the middle row, and stellar age, which is the bottom row. So the very smooth picture on the right is the Milky Way, because we have all this close-up detail. And the one that is still resolving on the left, basically, is this other galaxy, UGC 10738. And the exciting thing about this, there's a big question in Milky Way studies about how the thick disk came to be and whether thick disks are normal in spiral galaxies and all of that. But what they found in this galaxy is that it seems to have a thick disk analog situation going on. There is, high above the plane, there's a collection of old metal poor alpha-rich stars. And so this is very exciting as a first step. This is spun off into a whole Muse program proposal that went in last semester. So I'm very excited about all of this. Some science that we've done recently. So it's been a while since we did an in-person science meeting. So I took recent to have a fairly broad meaning, and this was from 2020 by Michael Hayden, who will be speaking later, taking disk stars and looking at what is the connection between metallicity, alpha enhancement, orbits. So the plot on the left shows you the vertical velocity dispersion, and the color coding is metallicity. And the metal poor stars have a big vertical velocity dispersion, which is what you expect. They're generally older. They will have been heated up over time. The plot on the right is the orbital eccentricity. And the stars don't separate quite as well in eccentricity, but there is still something there, that the stars that are more metal poor, that have been around for longer, have also come off of nice orderly circular orbits and been perturbed out to higher eccentricity. Come back. So anyway, we have models for how the Milky Way forms that we can compare this against, but we also have other galaxies where we have spatially resolved spectra, and we have Schwarzschild modeling of what the different populations, how they should be orbiting. And so we can actually take this and go directly to other galaxies, which is very exciting for us. One of the things that we've been really interested in is the connections between stellar abundances and age. There's this concept of chemical clocks. and which elements get created in which sort of events, and how does that build up over time. And so with a data set like GALAH, with several 100,000 stars, we can go and try to figure that out. So this is 20 different elements in the GALAH sample. The number in the top right of each panel is how many stars went into that panel. So the good elements, we've got 50,000 in. Ruthenium, we have 458, so don't worry about that one. But the x-axis is the age of the star, so old stars on the right, and the y-axis is the metallicity. So it's the same for every panel, and the color coding is the abundance of that element, normalized to the median of the distribution so that they all go on the same scale. And so some of the elements, obviously iron correlates perfectly with iron, right? So that's sort of your way to get oriented. Some of the elements gradient sideways, which means they don't care about metallicity, but they do care about time. And some of them gradient more vertically, and that says that they care very much about metallicity. They track very closely with the type 1a supernovae, for example. So this gives us a really interesting, completely empirical way to look at those models of nucleosynthesis and of chemical evolution and to see what's really going on. Very exciting. Sven Buder wanted to go get out of the disk. That was the disk, right? And he wanted to get into the halo. There's been a lot of talk about stars that have been accreted into the Milky Way from dwarf galaxies. And there's been a lot of debate about the right way to identify those stars. And so because you can get a group of Milky Way astronomers hopelessly sidetracked by asking which elements are best for this, right? And so Sven went off and did this for ages, figure out which elements are best. He made all these graphs, did all this mixture modeling, and figured out statistically what gives you the best separation between your different groups. And the answer is magnesium, at least in GALAH data, magnesium, manganese, and sodium. But he tried everything to figure that out. So we can use a plane of sodium abundance, magnesium, and manganese to say which stars are from the Milky Way and which have been captured from other galaxies. And when we do that, we have an avocado that Stu showed very briefly at the beginning. You can look at that abundance plane, sodium, magnesium, manganese, which is the top row. And the grayscale underneath is all the stars in the galaxy. And if you pick just based on abundances, you get that yellow group. If you pick just based on orbits, just kinematics, you get the red group at the bottom right. So the bottom row is a kinematic diagram that shows you angular momentum and radial action, which is basically eccentricity. And so you would expect stars that have been accreted into the galaxy would have funny orbits and funny abundances. But what you see is that when you select by dynamics, your abundances aren't very well selected. And when you select by abundances, your dynamics are not very well selected. And this is another one of those things that we can just get in endless loops about. So what Sven did was said, okay, we'll do them both, right? And so you get the middle group, which is correct in both aspects. And so in both cases, those are incomplete now. You've cut off things that are true according to one criterion and not according to the other, but it is less contaminated than it would be otherwise. So it is a starting point to go out, find out more about those stars, figure out better ways to identify their relatives and friends and where they came from and the properties of their original host galaxies and all of that. Ella mentioned the cosmological lithium problems, and I am pleased to say that we've solved the other one. And the answer is just that in order to solve the cosmological lithium problem, you need to find young metal poor stars. And there are no young, massive metal poor stars in the galaxy anymore because they all formed early on, but they were massive, so they're gone already. But with GALAH, what we can do is we can measure lithium abundance for slightly more massive stars that are around the turnoff, that are sort of solarish metallicity. And we can make a plot like this, which is metallicity, lithium abundance. And when Ella was talking about the fact that we measure lithium-7 and it's lower than it should be, that's the red points, right? And when you look at metal poor stars, that's what you see. But when you look at these slightly more massive stars, that they're elevated relative to the lower mass stars, right? And you can imagine just extending that line out to the left, nice and parallel to the plateau for the metal core stars. And in fact, it would line up perfectly with what you would predict from Big Bang nucleosynthesis. So the conclusion is those stars aren't there anymore, but clearly this is a good explanation for what happens. And clearly the lower mass stars have had some sort of process to dilute their lithium a little bit in the intervening time. So if massive metal core main sequence stars still existed, we would predict they would be on that upper line. Which is good because you don't want to be in a fight with the cosmologists. Big Bang nucleosynthesis is not wrong by a factor of 3, right? So it's good to be able to solve this. Come on. There we go. Okay, so we've been busy. We've been doing a lot of interesting studies. We've been writing a lot of papers. We've been keeping track of it. So Stu showed some publication statistics earlier for all of ASTRO 3D, which is great. Within GALAH, we've written 52 papers. We've gotten over 2,000 citations from over 1,000 papers, and also 167 other people who are not part of the team have taken our data and published papers with it. And this has been part of our science strategy from the very beginning, that we want to be the standard. If you want to know about abundances in the Milky Way, we want people to come to GALAH for that. And so we are thrilled to have this great amount of uptake in the community, to have that kind of engagement and trust in our data. So this is very excited about all of this. One of those 52 papers by GALAH turns out to have been the highest cited monthly notices paper in 2021 by 10%. Trust me. There it is. Above the Hubble constant. Right. We'll see if that lasts past 2021. But the point is, the work is getting done. The work is getting out there. We're delighted that people are using our data, reading our papers, all of that. We are making plans for GALAH DR4. We have a whole new way we want to do the data analysis and the probabilistic forward modeling neural network. Jargon, trust me, it's going to be really cool. One of the things we're adding is carbon and oxygen abundances. Gary mentioned earlier that we don't do that very well right now, but we are adding a technique for that. Now that we have most of the elements down, we're going back, we're filling in some of the gaps. So yeah, to come back to where I started, we are adding people, we have collaborations, we're taking new data, we're improving our analysis, we are getting good results, and we're also connecting well with our community. So, yay GALAH. Thank you.